In last lecture we have seen the equation of the motion of the SHM, and from that we have calculated the displacement, velocity and acceleration for the simple harmonic motion. Now simple harmonic motion is a motion of a particle in a forward and a backward direction on a linear line. Now when the S.H.M is starting from the mean position, suppose S.H.M is starting from this point where x is equal to 0 at time t is equal to 0, we can say that the simple harmonic motion is starting from the mean position. Now first let us study the equation of the motion for the S.H.M which is starting from the mean position. Now x is equal to a sine omega t plus alpha. This is the expression for the displacement for any kind of SHM. Now for this SHM which is starting from its mean position, let us put the value of x is equal to 0 at time t is equal to 0. So this x is equal to 0 and this t is equal to 0, therefore a sine alpha, or I can write sine alpha is equal to 0 or alpha is equal to 0. We know that sine 0 is equal to 0, therefore alpha is equal to 0. Now if I put the value of this alpha into this equation, I am going to get the new equation of the motion, or the for the displacement for the SHM which is starting from its mean position, which is equal to x is equal to a into sine of omega t, as this alpha is equal to 0 at the initial position. Okay, so when I write this, x is equal to a sine omega t. So we know that the rate of change of displacement with respect to time is nothing but the velocity. Now if I take the differentiation of this, I am going to get the velocity. So velocity will be a omega cos omega t, and the acceleration is the rate of change of velocity with respect to time, and when I take a differentiation of this, I am going to get minus a omega square sine of omega t. See, the graphical representation of the displacement, velocity and acceleration for the SHM starting from its mean position. Now see, when this SHM is starting from the mean position, the time period required for complete one oscillation, it is called as a time period. So let us call that time as a t. Okay, so this, let us call this phase as 0. Now there will be phase where this, I will call this as a phase pi by 2. So when the particle is starting from here, so this is called as a pi is equal to 0. This is a one phase. So when the particle reaches from here to the extreme position, then let us call this distance as a, which is the maximum displacement from its mean position, which we call it as amplitude. So this is another phase which we call it as pi by 2. Then this particle is coming back again over here. So this is called as a pi. Okay, and then afterwards, when the particle is coming over here, so this phase is 3 pi by 2, and when it is coming back here, so this is called as a 2 pi. The graphical representation of this displacement, so let us take this as a t, and here we can show displacement. So maximum value of the sine omega t, so sine value of the sine omega t may change from -1 to +1. Therefore the value of the displacement, maximum displacement, will change from a to minus a, or minus a to a. So let us see, let us call this as a minus a and this as a plus a. Now when the particle is at the initial position, okay, so at that time when this x is equal to 0 and t is equal to 0, so phase is equal to 0, and I can write this x is equal to 0. Okay, now suppose in a complete time period, the phase is changing many times. Now suppose if this t is a time, okay, which is a time required for the total one complete oscillation, so this total time period can be divided into t by 2. So this is t by 4, and now this is 3t by 4. So for this, the phase which is related to this, so this is pi is equal to 0. So this time period is represented by the phase of pi by 2. Then this is represented by pi. Then the third point 3t by 2 is represented by 3 pi by 2. And then this is represented by 2 pi. Okay, now by using these values, these are the values of this omega t. Okay, so when this omega t is equal to 0, sine 0 is equal to 0, therefore x is equal to 0 at pi by 2. When we put the value of this pi by 2, so sine of pi by 2, we know that sine 90 is equal to 1. So when this omega t is equal to 1, x is equal to a. Now let me show it here, a. So for the pi by 2, the value of this displacement will be a. Now when this omega t is equal to pi, which is 180, so when sine of 180 is equal to 0, therefore value of this x will again become 0. So let me represent the x value 0 here. When the value of this sine omega t is or omega t is 3 pi by 2, then this 3 pi by 2 value of this sine becomes minus 1, and therefore a becomes minus a. So let me represent it here. So let me call it as a minus a, and again it will become 0. So the graph will be like this. So this is a graphical representation of the displacement vector for the S.H.M starting from its mean position. Now for this diagram to draw, you must know how the time period is divided and what phase is related at a particular time. So the time period is a period required for a complete one oscillation, and the phase changes relative to that. So here the phase is equal to 0 means the omega t will be 0. Here omega t will be pi by 2. Here once again when it is coming back, then it must be pi, then 3 pi by 2, and then 2 pi. So the phase is changing 2 times for one complete time period. We can say that this omega t is nothing but equal to omega t plus capital T. So these displacement, whether it is a displacement, whether it is a velocity, or whether it is acceleration, they are repeating their values every after this 2 pi interval. Okay, so the remaining graph after this will be repeat itself like this only. Okay, so this much distance is very important, and the same will repeat after every interval of a time. So this was all about the displacement vector. Now if I try to plot the velocity, the same graph will be there. So this is t, so this t again is divided by t by 2, t by 4, and 3t by 4, which is related to pi by 2 phase, pi phase, 3 pi by 2 phase, and 2 pi phase. Now the velocity maximum value will be a omega, as it is a cos wave. Okay, so the cos wave, we know that this omega t will also take the values from minus 1 to plus 1. Okay, but as it is a cos wave, cos 0 is not equal to 0, so it will start from maximum a omega. So here it will be plus a omega, here it will be minus a omega. Cos 0 is equal to 1. Okay, so when this cos omega t is equal to 1, so v will be a omega, so the starting point will be here. So when this pi by 2, cos pi by 2 is 0, therefore this v will become 0, so the next point will be here. And cos 180 is equal to minus 1, so when this omega t, cos omega t will become minus 1, so v is equal to minus a omega, so the next point will come here. Now this cos of 3 pi by 2, so that is equal to 0 again, so the next point will come over here. and the finally cos of 2 pi is equal to 1. Therefore again it will come over, so this a omega. Now the graph will be like this, and the same graph will repeat after the same time interval of 2 pi or same time interval of t. Of course you can see that these 2 points are same, but here this velocity is going to the negative side, and from here the negative velocity is going to the point. So the velocity is decreasing, from this point velocity is increasing. Therefore even if the values are same, these two phases are different. Here, see here also in a displacement vector also, so these 2 points have the same value of the displacement 0 0, but after this point the displacement is going towards plus a, and from this point the displacement is going to the minus a. Similarly we can draw the graph for the acceleration. So this is t sum, so it is pi by 2, and the acceleration is changing, or it is taking the values from a omega square to minus a omega square. Now this is the acceleration. We can, as it is a sine wave, it is starting from 0. Sine 0 is equal to 0, sine 90 is equal to 1. So this a will be minus a omega square, so exactly opposite to the this displacement vector. And we have known the definition of the S.H.M, that acceleration and the force, they are exactly opposite to the displacement vector. Okay, so this is the graphical representation of the simple harmonic motion, which is starting from the mean position.